Okay, so for this problem, we're looking at max turn speed. I'm going to take a second to pause and let you read the problem statement. Feel free to resume when you're done. Okay, so we are given the radius of the curve, the coefficient of friction, and the mass of the car. Okay, and we're trying to solve for the maximum speed the car can have and still make the turn successfully. So Vmax. And when we say Vmax, what we mean is like the linear velocity, which when we're looking at a centripetal, when we're looking at uniform circular motion and centripetal acceleration, we mean the tangent velocity, like around the circle at each point on the circle, okay? So the car is going to be turning though, but just applying a constant speed, okay? And remember that turning force is what's creating that centripetal acceleration because we're sort of displacing that velocity vector in. We have this like delta V basically as it's rotating in, right? And that's what's causing that centripetal acceleration, is that change in velocity as that velocity vector is rotating in. Okay, that's why we're pointing in there. Okay, so just as an aside, sorry about that. Okay, so we're trying to find Vmax. So step one is we do our free body diagram. This problem was nice enough to draw it for us. A note on static friction. Static friction is going to be pointing in because we want to prevent the car from skidding out. So this is just the back view and this is the top view here. Okay, so here's our free body diagram. All right, so after our free body diagram, step two, as you guys are familiar, is always sum of forces. So we're going to do sum of forces in the, I'm going to call this just x and y here for this one. So we're going to do y hat, positive y, and then I'm just going to do x, okay, pointing in. So I just chose these to be my coordinate systems. Okay, so let's do sum of forces in the x and sum of forces in the y. So I want this maximum speed. So I have a coefficient of static friction. So the maximum speed that I can go is the one where this coefficient of static friction is going to be equal to my centripetal acceleration, basically. Okay, so let's see here. So sum of forces in the x, we have, let's look at the x direction. We just have static friction, so static friction. And then we are going to ask ourselves, always when we do these sum of forces in the x, what we're really solving for is F is equal to ma, right? So we're doing that sum of forces, and then we're asking ourselves, okay, what's the acceleration in that direction? And in this case, it's going to be a centripetal acceleration that's pointing in. So my centripetal acceleration, right, is going to be right, pointing in here and also like pointing in here. Okay, so we chose that to be positive. So sum of forces is going to be equal to mac, and we know this general equation, v squared over r. Okay, so that our linear velocity, right, is going to be equal to squared over r is going to be equal to ac. So we're going to be plugging this in just a later step. Okay, so sum of forces in the y, what do we have here? We just have n minus mg, and then we're going to set this equal to 0. The car's center of mass will not be accelerating up or down. It's on a flat track here. We're going to stay at the same height the whole time. Okay, so n is equal to mg in this case. Okay, now for this one, we're going to plug this one in. So we're going to say Vmax, right, squared over r. So this Vmax, this is a linear velocity. So centripetal acceleration is equal to the linear velocity squared over r. Okay, cool. So now let's rearrange some things. We also know F sub s is equal to mu sub s times n. Okay, so let's take and rewrite this piece. Let's use this expression for F sub s, and then we also know that n is equal to mg, right? Because we just solved for that. So let's say F sub s is equal to mu sub s times mg. Okay, so we're going to plug that in there. Okay, so let's take our sum of forces in the x equation, so just this one right here, and I'm going to rewrite it down here. So we want to plug in a different f of s, right? F of s, we found this piece here. So we're subbing things out for values that we actually know. U sub s mg, okay, is equal to m v max, okay, squared over r. Okay, cool. So notice that we can cancel out these masses here, which is kind of nice. So then I have mu sub s g, and I'm going to multiply by r, okay, equals v max squared. Okay, so the square root of, if I just sort of rearrange this a little bit, rg mu sub s is equal to v max. Okay, cool. So I was able to simplify and basically get an answer here for things that I can actually solve for. The mass ended up not mattering here. Let me just make sure that that is correct. Yep, the mass ended up not mattering at all. So we didn't even use it here. And we found the maximum speed that the car could travel. And we just ended up using our mu sub s and then r that we were given. So Vmax here is going to be equal to 13.4 meters per second if you plug those numbers in. Okay, so just to recap, we have a car traveling on a track with a constant velocity as it's moving around. So we have uniform circular motion. Because we have uniform circular motion, we have centripetal acceleration, okay? And we were trying to figure out the maximum velocity we could travel forward with and have the car not slip. So we want the wheels to be, to keep traveling forward on the pavement, and we don't want them to slip basically side to side. So if the whole car, if we take it and kind of like, if you imagine what I'm saying when I say slip, like imagine this is a giant hand and I push the car to one side and those wheels like skidded sideways. We don't want that to happen. So when we're preventing slip, we're just preventing that, okay? All right, so we set everything up. We set this up, we let the static frictional force offset the centripetal acceleration. So we set them equal and we solved for this Vmax. I know that things tend to be a little bit confusing because the direction of centripetal acceleration really throws people off, especially when it aligns in the same direction as your friction. Take my word for it that this is the correct way to do it. I'm sorry that it tends to be a little bit intuitively weird, but hopefully this problem makes a little bit more sense to you. If it does not, please leave a message in the comments.